welcome to this session. Now, as we have seen in the last class that we are basically solving the system performance. We were trying to predict the system performance, that is the permeate flux and permeate concentration for an osmotic pressure control filtration using the one dimensional model of mass transfer boundary layer, and the one dimensional model is also commonly and popularly known as the film theory model. Okay, so we have seen that ultimately we have written down the film theory model, and we got the one equation Vw is equal to K ln Cm minus Cp divided by C naught minus Cp, and the solvent flux through the porous membrane, that is the osmotic pressure model Vw is equal to delta P minus delta pi. And we have also seen, so let me write down those two equation, Vw equal to K ln Cm minus Cp divided by C naught minus Cp, and Vw is equal to Lp del P minus del pi. And we have also seen that how delta pi is related to Cm minus Cp as A1 Cm minus Cp plus A2 Cm square minus Cp square plus A3 Cm cube minus Cp cube. So, we have basically, so therefore, this equation can be expressed in terms of Cm and Cp, and this equation is also expressed in as another function of Cm and Cp. But there are three unknown, Cm, Cp and Vw, and we have two equations. So, we need to have one more equation. So, what is the third equation? Let us look what is the third equation. Third equation is basically a connective equation between Cm and Cp. So, what is the connective equations? There are if you look into the definition of real retention, is 1 minus Cp by Cm. So, this is one route how to connect Cp and Cm, solute concentration at in the permeate and solute concentration on the membrane surface. So, as we have discussed already that real retention is nothing but an intrinsic parameter of the membrane which connects the concentration of solute on the membrane surface and concentration of solute on the permeate side, and it is constant for a particular membrane solute solvent system. So, and we have also seen how independently the real retention of a solute and membrane solute solvent and membrane system can be estimated by conducting a separate set of experiment. So, therefore, real retention can be treated as constant. If you look into the expression of real retention, it can also be interpreted as a partition coefficient between of solute between feed and permeate side across the membrane. So, it can be interpreted that by that as well. So, if you estimate real retention from a separate set of experiment, we can connect Cp in favors of Cm and real retention. So, Cp can be written as Cm into 1 minus Rr. So, that is how we get a third equation or extra equation for Cp as a function of Cm. What is the second idea? The second idea is one can, instead of this relation definition of real retention, one can really use the solution diffusion model that we have already derived earlier. So, if we are talking about a nanofiltration system or a reverse osmosis system, we are going to use the solution diffusion model in order to invoke the third equation. If you are talking about the ultrafiltration or various lower cutoff of ultrafiltration or higher cutoff of ultrafiltration, then we will be invoking the definition of real retention in order to connect the Cp and Cm as a third equation. So, let us write down the solution diffusion model. Or there are other variants of solution diffusion model that we can also look into. So, this will be VW Cp is equal to B times Cm minus Cp. So, this is the solution diffusion model. This can be utilized as a third equation in case of reverse osmosis and nanofiltration, and in case of ultrafiltration we can use the definition of real retention to connect Cp and Cm as a third equation. So, let us look into the case of ultrafiltration first, because that will be given the an easy way of handling the system. Then we will be looking into the solution diffusion model, and after that we will be examining the various other cases of variants of solution diffusion model. Okay. So, let us continue with the osmotic pressure model. The third equation that we have already found out. Okay, let's write down the equations for to solve. We have three unknowns Cm, Cp and permeate flux Vw, and three equations now. Vw is equal to Lp del p minus del pi, which will be essentially Lp del p minus A1 Cm minus Cp plus minus A2 Cm square minus Cp square minus A3 Cm cube minus Cp cube. Okay. We have the equation of definition of real retention. Cm is equal to 1 minus Cp is equal to 1 minus Rr times Cm. There is a connection, and we have the film theory model. Vw is equal to K ln Cm minus Cp divided by C naught minus Cp. So, we have three equations and three unknowns Cm, Cp and Vw. Next, what I am going to write, I am replacing Cp as a function of Cm in equation 1. Suppose this is equation number 1, this is equation 2, this is equation 3. So, if we combine these two, we will be getting Vw is equal to Lp del p minus A1 Cm Rr minus A2 Cm square 1 minus Rr square of that minus A3 Cm cube 1 minus Rr whole cube. Since Rr is constant, A1, A2, A3 coefficients or osmotic pressure coefficient is constant, delta P is constant for a particular operating condition, Lp is constant. So, Vw will be a function of some function of Cm, and we can write down the third equation, the film theory model, as Vw equal to K ln Cm minus Cp. So, ln Cm times Rr, and this will be C naught minus Cm 1 minus Rr. Now, this will be another function of Cm. So, this is equation number 4 and this is equation number 5, and so now we will be having two equations and two unknown only, because we have eliminated Cp in favor of Cm in both the equations, and equation number 4 and equation number 5 are the two resultant equation. Now, what are these two equations? These two equations are algebraic equation, which can be algebraic equations, and they are basically connected coupled nonlinear algebraic equation, and therefore, these two equations can be solved using Newton-Raphson rule or Newton-Raphson method by a guess value of Cm. So, we use a guess value of Cm, and then we will be equating equation 4 and 5. So, if we equate the equation 4 and 5, we will be landing up with only one equation in Cm. So, comparing equations 4 and 5, we can equate them out. So, this becomes K ln Cm Rr divided by C naught minus Cm 1 minus Rr is equal to L P del P minus A1 Cm RR minus A2 Cm square 1 minus RR square of that minus A3 Cm cube 1 minus RR cube bracket close. So, this will be a nonlinear equation in Cm only unknown is Cm. We can cast it in the form of h times Cm some function is equal to 0. So, if you take the right hand side on the left hand side, then we can write it in the form of some function of Cm, a nonlinear function of Cm, algebraic equation. So, therefore, this can be solved using Newton-Raphson method. Iteratively. So, once we get the value of Cm, so what will be the output of this? Output will be the Cm. Once you get the value of Cm, you can get the value of Cp as 1 minus RR times Cm, and one can get the value of permeate flux as K ln Cm minus Cp divided by C naught minus Cp. We know the value of Cp now, we have already estimated. We know the value of Cm, we have estimated from this. C naught is known, K is known, Vw can be estimated. So, therefore, this is a predictive method of calculation of permeate flux and permeate concentration as a system performance for one dimensional modeling of mass transfer boundary layer and hooking it up with the flow through the porous media for a cross flow filtration system. So, this will be giving you a very brief, very good idea about as a first hand calculation for having a system performance, and this can really be done in an entirely predictive mode, because we have not, there is no adjustable parameter. If we really know the solute diffusivity, if you so what are the input parameters of this problem? The input parameters of these problems are the operating conditions. What are the operating conditions? The operating conditions are delta P, the transmembrane pressure drop, feed concentration, and cross flow velocity, that is U naught. These three values are operating conditions, we are already setting them, so we know their values. Another important operating condition is pH of the solution, and how the pH of the solution will be affecting. pH of the solution will be affecting the osmotic pressure of the solution. So, osmotic pressure relationship is known to us, pi is equal to A1C plus A2C square plus A3C cube. These osmotic coefficients A1, A2 and A3, they are known to us. So, this physical what are the other transport coefficients you require? The other transport coefficients you require: density, viscosity and diffusivity. We are assuming them to be constant, and their values are known to us. What are the others? The other two parameters should be known to us. These are basically the membrane performance parameter. One is the one indicates how porous my membrane is, that is the permeability of the membrane. Another was the how selective my membrane is, that is the real retention of the membrane. So, in the earlier classes we have already seen how to estimate membrane permeability and the selectivity of the membrane independently, and therefore, using these values only, one can really solve permeate flux and permeate concentration in a predictive mode. There is no adjustable parameter in this model, and a prediction can be really done. And in the process, another parameter, the membrane surface concentration, solute concentration at the membrane surface can be estimated as well. So, therefore, one can really estimate what is the extent of concentration polarization. This is also known as the polarization modulus. So, what is the polarization modulus? Polarization modulus is known as by this ratio Cm by Cp divided by C naught minus Cp, or for a partially retentive membrane, that is RR is not equal to 1. For a completely retentive membrane, Cm divided by C naught, for RR is equal to 1, where Cp is equal to 0, and in this case Cp is not equal to 0. So, typically the polarization modulus for the osmotic pressure controlled filtration will be around 2 to 5 in most of the cases, and it can be as high as 24 or greater than 20 in case of solutes like dextran. So, this polarization modulus will indicate the extent of concentration polarization that will be occurring within the mass transfer boundary layer, or the polarization, the concentration of solute will suffer within the mass transfer boundary layer. In the next, we will be seeing as how we can overcome the assumption that the solute the transport coefficients, the constancy of transport coefficients. Now, as we have discussed earlier, the various transport coefficients those are involved in the system are density, viscosity and solute diffusivity. Now, all of them are functions of concentrations. All of them are functions of solute concentration. Out of these three, rho is the weakest function of concentration, followed by the diffusivity. Diffusivity is a slightly stronger function of concentration in some cases, and viscosity is the strongest function of concentration. In fact, viscosity is an exponential function of concentration. Viscosity increases exponentially with the concentration. So, therefore, the if it so from the values of polarization modulus, we can see that the concentration polarization becomes very dominant in some cases, in case of some solutes. Therefore, the solute concentration may suffer a 4 folds up to 50 up to 30 folds to 20 folds of feed concentration. So, therefore, the transport coefficients or transport properties will be suffering the most, and out of these transport coefficients the viscosity suffered the most. So, therefore, one has to invoke the viscosity correction factor in order to rectify the mass transfer coefficient, so that the property variation with respect to concentration is taken care of. How that is done? That is done by all of us know probably about the Sieder-Tate correction factor. So, property correction for variation with concentration. This is known as the famous Sieder-Tate correction factor, and these are included in the Sherwood number relationship. Sherwood modified is Sherwood 0 mu bulk divided by mu at membrane surface raised to the power 0.27. What is Sherwood knot? Sherwood knot is basically the basic Sherwood relationship that we have already discussed for the Liebig equation for the laminar flow through a rectangular channel. Sherwood knot will be 1.85 Reynolds Smith dE by L raised to the power 1/3. For what is the Sherwood knot for the tubular flow? 1.62 Reynolds Smith d by L raised to the power 1/3 for the laminar flow. For the turbulent flow, Sherwood knot will be 0.023 Reynolds to the power 0.88 Smith to the power 0.33. That is the those are the basic Sherwood number relations without any correction factor. So, what is the modified version of Sherwood number? The original Sharut number will be multiplied by the viscosity at the bulk concentration divided by the viscosity at the membrane surface, solute concentration at the membrane surface raised to the 0.27. And since we have already talked about that viscosity is an increasing function of concentration, then since mu b is equal to mu evaluated at C is equal to C b and mu m is evaluated is equal to mu evaluated at C is equal to C m, and we all know that C m is much greater than C b. So, therefore, mu m has to be greater than mu bulk. So, therefore, the factor mu b by mu m raised to the power 0.27 is less than 1. So, therefore, this modified Sharut number after viscosity Sieder-Tate correction factor will be less than the value without it. So, modified Sharut number will be less compared to the Sharut number without Sieder-Tate correction factor. So, that is how the so therefore, the mass transfer coefficient will be decreased. Mass transfer coefficient is less than less after incorporation of correction factor. Okay. So, next, so that is how the system performance can be predicted in terms of by taking care of property variation within the mass transfer boundary layer. Now, I would like to say one more thing is that if variation, if one tries to encounter the concentration variation on the properties like density as well as the diffusivity and then viscosity, all quite important, if they are quite important, then one can write the Sieder-Tate correction factor as SH modified is equal to SH naught. One can write, one can combine, there is a non-dimensional number that will be combining all these three properties, and that what is the number? The number is Schmidt number. So, Schmidt evaluated at bulk divided by Schmidt evaluated at membrane surface raised to the power 0.27. So, if one wants to consider the property variation of all density, diffusivity and viscosity, then one can include the Schmidt number at bulk concentration divided by Schmidt number at membrane surface concentration raised to the 0.27 as a Sieder-Tate correction factor. After this, what we will be looking into? We will be looking into some simplified versions, simplified cases for osmotic pressure control filtration, because we have already seen that in an actual case the solution has to be an iterative one through neutron reduction technique. Now, let us look into some of the simplified cases. Controlled filtration. So, the first case is we consider for all the cases osmotic pressure is a linear function of concentration. So, when the osmotic pressure is linear function of concentration, actually if you consider osmotic pressure as a polynomial of concentration, that will include the nonlinearity in the governing in the system, and that will be leading to that will preclude to obtain the analytical solution. So, let us look into some simplified cases where an analytical solution is possible and things will be functional variation of the independent variable with respect to the dependent one will be clear in front of the eyes of the readers. So, let us consider osmotic pressure is a linear function of concentration, and when this case can be can arise, this can arise in two cases for the salts and for dilute concentration of solutes. Okay. So, if that is the case, then we consider the case number 1. First, no concentration polarization. when the concentration of polarization can be neglected if someone has very high turbulence in the system. If the turbulence in the system is very high, then the mass transfer boundary layer thickness will be gone, and the whole mass transfer boundary layer will be properly mixed up. It is a thorough mixed up system, and there is no polarization of concentration from the bulk to the membrane surface. So, there exists no concentration of polarization, everywhere it is the bulk concentration. So, how will you model in that system? In that case, Cm is equal to C naught, and one will be having exponential Vw by k is equal to 1. Okay. So, permeate flux can be represented as Lp del p minus del pi, and if you write del pi will be pi m minus pi p. So, it will be b Cm minus Cp, and Cm is equal to C naught in this case. So, Lp del p minus b real retention times C naught. So, we know all the values, we know the Lp, we know the delta p, that is the transmembrane pressure drop, we know the b, that is the osmotic coefficient, real retention is known to us, fit concentration is known to us. So, we can get what is the value of Vw. So, once you know the value of Vw, and since Cm is equal to C naught, from the definition of real retention, one can get the value of Cp as Cp is equal to Cm into 1 minus real retention, and Cm is equal to C naught in this case. So, therefore, one can get a system prediction quite easily in the case when no concentration polarization, where the turbulence is very high in the system. Okay. I stop here in this class, and then we will be going to the next session, looking into some more simplifications, and then we will be moving over to various other formulations for reverse osmosis nanofiltration system, where the definition of real retention will be replaced by the solution diffusion models and various variants of solution diffusion model in order to get a more realistic situation. Thank you very much.